Hi, good. I was about to say good morning. Good afternoon, everybody. I just got out of bed, so good morning to me. So I'm David, and I have arguably made my career from fixing kind of broken or damaged systems, or kind of more importantly, taking systems and turning them into good, and occasionally with the right tailwind and the right people and the right phase of the moon, occasionally turning them into legendary systems, the ones that survive, the ones that pay the bills, the ones that keep everyone gainfully employed, that people eventually grow to hate, right? Like those kinds of systems. And this talk is about that process, really, about how the size and weight of the systems that we build is something that's often quite hard to comprehend, and how it has a lasting effect on the kinds of software that you design and how it interacts with the people that maintain those systems. So I want to start with something we can probably all understand. Okay, so I want a show of hands. Who in here can show me how long a 30 centimeter ruler is? Yeah, you got that in your head? Like, it's like that, right? Like everyone knows how long a 30 centimeter ruler is. Okay, hands up if in your mind's eye you can visualize a mile or a kilometer. Yeah, a couple of people. Just out of curiosity, someone that raised their hand, how do you visualize a mile or a kilometer? No? No one? Okay, I'll tell you my story. So for me, the house that my mother lives on is on a road with a bridge at one end that's a weak bridge. And it says, weak bridge in a quarter of a mile. So I know that up and down that road a couple of times is a mile. And it's kind of faintly ridiculous. But I think it's a really useful illustration of the way that humans relate to scale, right? We tend to internalize examples. All right, how big's a megabyte? Right. How do you think of that? To me, and this probably ages me like precisely to the day, a megabyte is a minute of 128 kilobytes MP3 music that I stole from Napster, right, basically. I mean, it's actually 960 kilobytes, but like we can round up those 40 kilobytes. A gigabyte? Just a bit less than an MP4 file of a movie at 720p from the Pirate Bay, right? And you'll notice that I'm getting a little bit less accurate as I go with these examples. But I think I can conceptualize via analogy digital storage across mediums, mostly due to like a lifetime of having really been able to intuitively understand the size of data in computers. But there are really two problems with this. It's basically why this meme exists. Right? Like you have no idea what a billion is. Like you might think you do, but you really, really don't have any idea what a billion is. Or this meme, because we've seen a lot of different versions of this recently, trying to explain why billionaires with access to government and technology is probably a bad thing. Yeah. But the next problem is even more complicated, right? And that's that the size of your software in terms of the amount of complexity that it can contain and the capabilities that it can express is not directly related to the number of bytes it occupies on your disk, because complexity really explicitly is not the same as raw size, right? This is, we've seen this time and time again. Measurements of size, things like raw lines of code, doesn't capture like the essence of the software that you're maintaining. Directories, components, the number of things, they're nothing more than like rough indicators of scale. But they just don't capture this concept of complexity or accurately describe the challenges of working with a code base. Now, complexity explicitly is a measure of how hard it is for your brain to compute or internalize a system. That's kind of my shorthand for it. Not how much code there is to read, though a measure can often help as a leading indicator. And this is basically why you think that file system APIs are simple. Right, despite the fact that they bury the hidden complexity of file systems and spinning disks and SSDs and operating system interop, but to you it's just a string and a byte stream, right? So this difficult mix of size and complexity and scale wreaks absolute havoc on the way we design our systems, because getting it wrong leaves you carrying this burden of complexity that often will outmatch your organization and leave your software to kind of atrophy and stillness. And this same problem affects lots of different aspects of software, from understanding complexity to design to estimation. They're all fundamentally related to how we're very, very bad at understanding scope, size, and scale. So a couple of years ago, I wrote a talk called Intentional Code, and in it I used this one phrase to try and describe complexity, and that's that the complexity of your software should be at most as complicated and ideally less than the problem space it inhabits. right? Like that's what good system design looks like to me. And I said it to try and capture this idea that if you're building complicated answers to simple problems, you're likely backing your implementations into a corner. And the more I've thought about this idea over the years, I've reached this complementary idea about what gives software this feeling of being big or too much or the wrong size. Because a lot of the way that you respond to software is when you look at it and you get that like inherent sense of dread when you open a thing that like kind of looks wrong and feels wrong. And that's, to me, that it's the surface area of the software and systems that we respond to, like the observable surface area and not actually the depth of the complexity contained inside of them. And I basically think that humans are affected by the surface area, the total sum of interfaces that they're exposed to, the number of moving parts and the number of data structures, rather than the depth of an abstraction. And controlling that surface area, your software design, your subsystems and your modules, is important for any system that survives. Like, you have to be mindful of this dimension. And this is, again, the reason you think code that accesses the file system is simple, while you will look at thousands of lines of boilerplate, actually simple enterprise, copy, pasta, mulch, and think that that's complicated, when actually it's simple but repetitive, right? And we make these poor trade-offs every time. And the real epiphany for me, once I stepped back from software implementation into thinking about this in terms of large-scale system design, is that I saw the exact same thing occur there at a larger scale. Now, architecture tries to solve this surface area problem by containing complexity in various ways. But is software architecture in its current form really the answer? Like, one of the reasonable answers to the question, what is architecture, is that it's the big decisions that you make when you build systems, or the decisions that are difficult to unmake once they are made. And I could probably talk for an hour about all the competing different definitions you can get if you ask any architect, what is architecture? I just kind of come back to the idea of large-scale design because everyone's very inconsistent when it's not really a discipline that's well documented. Now, to me, architecture is explicitly concerned with trying to contain the complexity in the design of systems. So, by definition, it's a significant part of the job to attempt to contain, control, or provide a good answer for complexity that comes with growing a system to scale. Now, the path to containing complexity leads us to some really, really weird places, and it can be especially damaging to the architecture of our systems with the way that we often build with our processes today. Now, the system that I'm currently building in my day job, it's in financial services, was basically forged in the shadow of a failed attempt to understand complexity and a failed attempt to reach the right size of a system. Like, this is the pain I feel every day. And the original design of that system was basically born at the height of, I like to think of it as the misunderstanding microservices boom. And it was one born of dictatorial, tyrannical rules. Everything is a microservice. Everything is a serverless function. Everything should use Cosmos DB for storage. All X's are Y. Lots of like proclamations of complete uniformity. And it's taken the teams I work with like literally half a decade to start to course correct some of the pain these really blunt design instruments have caused them. I kind of think that uniformity in design is like this kind of original sin of software architecture, where like it looks neat so people think it's good, but that's not really the goal. Because in trying to make everything uniform to contend with perceived complexity, the real outcome is systems that don't fit in their context at all. And they end up brittle and they eventually fail and stagnate. So designing your systems around technology choices specifically, not outcomes, is like this perennially bad idea that is bad every time I've ever seen it happen. And this is the pain I feel. And the problem is I've encountered trying to consolidate this kind of fundamental technical misunderstanding of scale reminds me of this this other famously shared system design. So, has anyone seen this before? Curious. Maybe it's past a time now. So, Monzo, the challenger bank in the UK, published this maybe 2017, 2018. And at the time this was published, which was, again, at the height of the microservices boom, Monzo were talking about having 1,500 microservices, and the things that they publish today put that number up closer to 2,800. And when I say that, I can feel everyone's kind of like stomachs churn of just like, oh, that's terrifying. And the truth is this, I'm hesitant to criticize somebody else's system design, especially one that I'm not responsible for, because everything exists in a context. But I'd feel deeply uncomfortable personally about owning a system that carries this amount of resting connectivity complexity. Like the number of things that can go wrong here by default is tremendous. And I feel like the Monzo diagram received a lot of criticism from the community for two reasons, really. Firstly, if you don't live inside of it, you have no context. It's very difficult to imagine what design it could exhibit that would be suitable to maintain someone's mental model of a bank. Like the idea that that's a bank is like absurdist humor to me. And this isn't specific to Monzo, right? I have extreme sympathy because banking is incredibly complicated, but the surface area of it that most people are exposed to is money in and I tap my card, right? That's basically what people think banking is, and it just isn't that thing. But secondly, I think there was some valid criticism directed at it because people thought it appeared to celebrate this degree of distributed complexity, and when in reality, I think it was actually intended to be closer to to them saying, hey, look at how we survive this complex beast of a system that we've built. Not everybody should run out and copy this thing and do this is awesome, right? And I think unfortunately the technology world is full of kind of systems envy, where people try and copy other people's homework because they think that will give them the answers that they're looking for. So I've got the sense in recent years that as the technology industry has gone through the kind of the growing pains of large-scale system design, and as more and more people have to engage in internet-scale systems, that like loads of mistakes, including the ones that I've ended up trying to resolve, have really been the side effect of both the difficulty of understanding scale combined with the literal application of simple soundbite advice given on stages by boring middle-aged white guys at conferences. Awkward. Yeah, but you know, the truth is, basically soundbite advice always oversimplifies design problems because in the last 15 years, we've always been able to just add more components to a system, right? We're 15 years into the popularization of cloud computing, and you can literally just turn that dial up to more and pour more stuff in. And I think this has had the really unfortunate problem to get our heads around that something that generally has been good for us, the loosening of constraints by the commoditization of cloud infrastructure, has equally been harmful by, ironically, removing the constraints that forced us to do design through necessity. And you no longer have to find a constrained solution because more can just be more, other than maybe this month where nobody has any memory anymore. And I hope you're not building computers. So if the traditional tools of architecture seem to be failing us and lead to these like explosions of complexity, how can we chart a course of large systems without making those same mistakes? So this line of thinking really took me on a bit of a journey of having to reconsider what the role of design and of architecture is in the current software ecosystem. Now, I always remember this rough quote from an interview between Harrison Ford, about recording Star Wars. Now, it was not a tech talk without Star Wars, right? So George Lucas made this like beloved sci-fi franchise. Everybody knows what Star Wars is, but he was notoriously a fucking shitty writer, right? And it was claimed that much of the success of the original Star Wars films was directly attributed to his then wife, Marcia Lucas, who became a Hollywood script doctor after they split up. It's no surprise that when the sequels were made, it was after his divorce, and that's the dialogue you got. Sorry, George. So there's this great quote where, as he tells it, Harrison Ford was struggling with a series of takes on one of the Star Wars films, and he got into an altercation because Lucas was like pushing him to re-record, and he stormed off set shouting, "George, you can write this shit, but you can't say it," right? And it's always amused me because it kind of it implies a specific dynamic. And I think it's kind of really similar to the difficulties that architecture and implementation and programmers kind of face, where the way that you describe a system doesn't survive its first meeting with reality most of the time, right? Like it's just not how it works. And I think thinking of architecture as a discipline distinct from code is a mistake, precisely because of these kind of symbiotic code-dependent disciplines, right? If you invalidate one, you break the other by default. Bad architecture ruins code, and bad code ruins architecture. So anyone that looks at it from only one perspective will always be doomed to get it wrong. So it's kind of a tough spot, right? Systems are bigger and more complex than ever. The constraints that previously were used to keep them contained are loosened by cloud computing, and traditional architecture through the lens of systems like TOGAF buried itself in so much bureaucracy that it's so far away from the actual work that most people don't find it useful anymore. But the systems and the problems still exist, right? And they're growing organically while all these other things are failing around them. So I want to talk about some of the tools that I use to try and bring some sense of calm back into the kind of chaos of this over-designed, over-distributed, brittle ecosystem that crops up again and again and again. Okay, so firstly, important golden rule, design is for everybody. Everybody does design now. And rejecting traditional big upfront lines and boxes processes doesn't mean you should stop doing design. It actually means the opposite. You should be doing more design continually. Your system has a design, much like Conway's law, right? A design will emerge if you don't think about it. And then you'll be stuck with an accidental freehand design that you can't reckon with. One of the most important changes in my day-to-day working pattern was to try and invert the power dynamic between the people holding architecture and design jobs and turn them into people that help facilitate good design rather than the people that provide designs for people to implement. And like my job title in my day job is Director of Architecture, and I try and not direct architecture, right? That's the gambit. And I think it's vital in any organization because it helps scale out the ability to design solutions while putting people who hopefully speak like a shared language of design right there with the people doing the work. And I think you have to accept that all of your designs exist in a context, and people often don't articulate or reason with this. And your context is your business and your volume and your scale. Now, I've seen a lot of businesses like commit tremendous acts of self-harm by spending huge amounts of money designing systems for businesses that they are frankly not in, right? I've seen people overextending themselves and saddling themselves with both business and technical debt, operating complex things because they were dreaming of a future rather than the place they were at. And you know, I always feel like a system design should be good for 2 orders of magnitude growth and no more, right? The best system designs are simply the designs for the problem you have. And the second best system design is for the problem you're about to have, not the one you're going to have in 10 years' time. And I think accepting that is understanding that every design is foundationally, it's temporal, right? Designs exist in a place of time. And you should expect it to change. Because a design that doesn't change wasn't a perfect design. It's more likely that it's a design that's constrained you without you having realized it, or was too impervious to change. So I try and establish like really good ground rules for people to make sure that people engaging in design, whoever they are, know who and what they're designing for. I want them to write it down, yell it out loud, to have a goal, right? So in my day job, I have this one phrase, and I've used this one phrase for 5 years, that I use to drive out every design in our system has to walk us closer to the one phrase. And we build a credit card platform. And whenever anyone asks what we build, I say we're building a credit card platform for 10 years in the future when credit cards don't exist. And it perfectly summarizes the goal, right? And I think you all have to find that statement of intent for the systems you're building. Like, what are you actually doing? And it has to be so ubiquitous in your business that you can ask any engineer on the floor and say, what are we building? And they will basically give you the same answer or a very, very slight variation on the theme. Because if you can't do that, you end up building disparate systems that don't navigate you closer to that place. Now, the next most important thing to do once you've established that context that your system exists inside of is to express the common set of trade-offs that you're most comfortable with. Now, that's all software design really is, right? It's a set of trade-offs where you are most satisfied that the one you pick covers the majority of problems that you know you need to solve. Every design decision is just a trade-off between something. And you have to give your teams a uniform language to describe them so they don't find themselves making seemingly arbitrary design decisions. Now, this isn't new thinking, right? So this is ATAM, Method for Architecture Evaluation. Now, this was developed in the year 2000 at Carnegie Mellon University, and it was presented as like a boring old architecture discipline. At its core, it's literally just like, here is a process to think in trade-offs. Now, I'm not here to sell you a process, and the irony with this being developed in the year 2000 is nobody reads shit like this, right? Like, they just don't know, like, who writes like that? So, here are some examples of the kinds of trade-offs that I staple to the wall, sometimes physically for people. We start with the obvious things: consistency versus latency, cost versus performance, availability versus cost. Basically, everything versus cost is the truth. But there are some more subtle decisions that you can take that often are subconscious. So fidelity versus speed is a common thing that people don't realize that they are making, but they make this trade often. Interactivity versus automatability, stability versus feature richness. And it might seem weird to evoke the Agile Manifesto when I'm talking about design, but one of the things that the Agile Manifesto did really well was have a format of trade-offs. You know, the format really works. We prefer this over this thing. It doesn't mean we don't want some of that thing, but mostly choose that one if you have to choose. And the reason you do that is because it's basically impossible to know exactly which trade-offs you or your teams are going to be making as they design some software or system. So I also like to articulate the characteristics of the eventual design that I prefer. So for example, let's say you're designing a system that deals with vulnerable customers. Now this is like a real thing in my business, right? We're a consumer credit card company, and if people are unwell and we chase them for debt, we're breaking the law, and so that should be illegal. Like literally, fuck us, right? If we're harming people. So you can come up with rules. For example, no feature should cause harm or duress to customers. Right? So articulating that characteristic helps you guide the design decisions that you bake into your system. So if I was faced with two competing designs, so let's imagine if an error occurs, one where a customer would be forced through a support process. Maybe they were double charged and we have to refund them. Now, I think that's harm. The other option could be, well, when a failure occurs, it could just cost us some money. If we believe in doing no harm, we always pick option B, even when it might seem like the other solution is more elegant or more effective or easier, right? And understanding those characteristics help you kind of keep, again, the goal, but also the people that are interacting with your system in the center of it, right? And it helps teams choose between two effectively equally valid trade-offs. So it sounds funny, but I think I learned this lesson from a silly pirate video game. So I spent a lot of time over lockdown, I suppose, playing this game called Sea of Thieves. So it was made by Rare, you know, the GoldenEye people. And I was watching some of their behind-the-scenes development logs, and I thought the way they articulated things that they put in the game as tools, not rules, was like a really excellent reduction of the kinds of things you need to do in an organization to establish good design. So as part of establishing your shared language of trade-offs, it's useful to have some like archetypical designs for the boring things that you do all the time. And I think that's where like more traditional architecture comes into play. It's a thought I've been coming back to more often as the system that I look after kind of sprawls out in front of me, that localized design will often be novel because the system is of such a size that one cohesive design philosophy becomes basically impossible to maintain. Like you cannot force coherence onto a large system that grows at different rates. It just doesn't happen. Because if you try, you will go slow and you will eventually stop. But I think what we can do is we can give people touch points, like a few patterns or tools to communicate between each other who are effectively living inside the same software ecosystem. And the more you equip them with tools, sometimes those tools are patterns and practices for implementation, or maybe protocols that you design, or processes to interact between the humans. You enable the novel design to exist in the corners of the system where people can really innovate, right? So as long as the outside edges of the boxes all kind of look the same and work the same, let people go nuts, right? Let people do novel design, let people innovate. And that's because rules exist solely to introduce constraints to a design. And there is some utility to that, right? Like you don't want people worrying about logging or deployment, right? Like you don't want novel design and those things. Do them once, solve them forever. But those constraints are the kind of constraints that give people the freedom to use their mental cycles to do other interesting things. So everyone gets really focused on process, especially in business. And it's my belief that your design process should be as cheap as possible, right? That's the best design process. That means you should use methods that are the most appropriate for expressing the designs you're trying to articulate. Like sometimes, sure, it's boxes and lines, right? Like sometimes do the boxes and lines. But actually, oftentimes, I prefer the teams drop into prototyping mode. And I always think things like HTTP APIs are a great place to illustrate how actually just going and hashing out some actual software is better than spending ages drawing boxes to represent them, because the ergonomics of the use of those APIs is actually one of the defining characteristics of their design. So like, use the thing we can do in software. Code is cheap. Like, write it, throw it away, feel it out, experiment with it, find it, rather than spend ages trying to design it on paper and then slavishly map it into another format. And like, you could do all that stuff on the whiteboard, but you would probably miss how it feels to use. Like, some things are not real until you see them. And I think one of the failings of traditional architecture is it became so kind of process-focused and so rigid that it almost disposed of like software's great superpower, that it's like just cheap to change software. You can always revert, you can always go back, you can always go forwards. And this is simply because no design meets implementation unharmed. It's never happened. I've been programming for 31 years, and I've never seen a design that was written on a piece of paper that was then programmed that was the same. I mean, maybe it's happened to someone, but you're probably smarter people than I. And I think it's also why it's not advisable to center yourself or a team in the middle of the design process. Because you can do it, but you're making a very distinct trade-off. Speed and bottlenecks for uniformity, right? So you get the mental model of one team. And it might seem like a good trade-off to make when you're starting designing a system. Go slower on the bigger decisions to make sure that they're all the same. And it kind of works to a point, but eventually your system then outgrows you. And the worst thing about it is when the system outgrows you, you will have taken all the opportunities for other people to learn when the stakes were really low. And only when it's really hard, you say, hey, everybody, now you're all doing design. And they're like, fuck, we don't even know how to do this. And I think that's the trade-off that traditional ivory tower architecture made, right? And it's why it failed, because it disenfranchised and basically took the education and the practice away from the people. So where does it all go wrong, right? Like back at the start of this talk, I was thinking about how so many systems seem to kind of swing and miss at this. They fall into the foibles of dictatorial uniformity in design, rigidity, and this like myth of prediction, where they form systems thinking that they know what the future of their business looks like. And it just begins to weigh everything down. So first, we need to talk about like the core crime of boxes and lines and traditional architecture diagrams. But more specifically, it's literal interpretation into over-decomposed systems. So diagramming is like one of the most useful tools you have to visualize things, right? Engaging your visual brain apparently works differently. I'm not a brain scientist. But one of the unfortunate side effects of drawing dungeon map diagrams of a system is often when you hand them to an engineering team, they will interpret each one of those steps, and those steps may be subsystems or processes, as like physical deployable units, right? And in my teams, I regularly stop people from subdividing obvious systems. Like, it's very easy in programming to be like, oh, let's split this thing up, split this thing out. Single responsibility, you hear people say it all the time. And often that's just because the boxes and lines diagram they're looking at contained a series of logical steps, right? But the truth is this, every additional component you add to a system is very, very expensive. It does not come for free. And even if the cost to like infrastructure is marginal, what people don't realize is every time you make a component, you're doing repository management, documentation, build pipeline, security scanning, patching, testing, verification, runtime latency. All of these things are the hidden costs that you get every time you make a new system. And taking a step on a diagram and extracting it out, either through some kind of slavish adherence to single responsibility or to match a design, just often has all these second-order costs that far outweigh the benefit. Right? Just almost all the time, it's a poor trade-off. And one of the things I try and help the teams I work with understand is that when is the right time to split things up? Like, if you shouldn't do it, when should you? So in my view, unless the parts of a design have either an order of magnitude difference in their usage or scale, different deployment characteristics, different traffic profiles, or different failure and recovery characteristics, you're basically paying all of the costs for zero benefits at all. Right? Those are the reasons you should split things out. And I've kind of noticed when I've been working with teams that the most attempts to split up systems are often secretly attempts to hide, or at least move kind of out of sight, out of mind, technical debt that's accrued in an existing system without really thinking about solving it. It's basically, oh, that's an ugly thing. Let's put it over there so I don't have to think about it because it's scary, and then we can just look at this bit. And that kind of fear is always the wrong decision, right? I have a friend that always says, conflict deferred is conflict multiplied. And I think it's exactly that. It's just people hiding from the problems, and the correct way to solve ugly pieces of code and bad design and technical debt is to address it, not to pick it up and put it somewhere else, right? Now, I personally like to think of systems in terms of fault boundaries, which I suppose is really my reinterpretation of like DDD-style microservices. So I use the term fault boundaries to escape the trap of over-relying on the term service. You know when we have these words in technology that cease to mean anything because we use them so much? Service. Service doesn't mean anything anymore. So inside a fault boundary, things always fail together. And increasing the resilience inside of a fault boundary has no effect on the availability of the system at all. And often, splitting things out from inside that fault boundary into a finely grained set of services is a poor design trade-off. And that's something I basically have stapled to the wall when I talk to people. Like, don't split that up. You're not actually solving a problem. You can identify the fault boundaries in your systems really trivially by just asking the question, what else doesn't work if this fails? Because all the things that don't work when that fail are secretly just the same thing, just part of the same thing. So if you see a lot of moving parts that fail together, they're probably best served as being one logical deployable unit without any of the buffers or inter-process hops or SOA frippery between them. Now, people also often use scale as an excuse. So people will say we need to scale as the reason to decompose a system, but without really a tight definition of what the word scale really means. Now, again, in my view, there are only really three kinds of scale. One of them is fitting more users around your system. The other is fitting more programmers around your system, which is often the reason people split things up, actually, and fitting more features into a system. Now, I find it useful when people say they want to do some subdivisions in a design to ask them which one of these are you answering, which one of these problems is it you're solving, because it basically has to be one of them. And often I will find that people are trying to meet some kind of theoretical scalability constraint or goal that their system actually doesn't need to satisfy. Okay, so if understanding scale and fault boundaries are like the good reasons to decompose software, yet people often reach for decomposition as a reaction to existing technical debt and accidentally increase the complexity of a design, we're kind of forced to answer the question, where is the right place to contain complexity, right? So I have two answers to that question that have always served me well. First is very traditional. Modularization and abstraction inside of an application is the design tool you have to contain complexity. So when you're tempted to decompose or subdivide system components, first ask yourself, can I meet the same goal I'm attempting to reach by simply designing a better abstraction or module boundary? Because if you can, you should always start with that first. Do that first before you build a system. My second answer, a bit stupider, never, ever, 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 ever put the complexity of your system in your infrastructure, right? The least debuggable, most pain in the ass, least reproducible, expensive thing, that's how you get Kubernetes, basically. And nobody wants that. It's like a weird venereal disease. Sorry. Hater number one, CNCF. Okay, so much of getting to the design of a system right is about resisting the surge to over-design and about resisting premature decomposition. Well, what you really have to do is accept the truism that all architecture is evolutionary, whether you like it or not. It's a fact. And the only real constant is that you don't know. right? You don't know. You don't know anything, really. You don't know that your system is going to have to change. It will change as it responds to the changing needs of the people using it. Your business will change. Everything will change. Change is the only constant. And you have to understand that because your context will change, there's only ever a good design for now, right? And that's kind of, well, it's the foundation of evolutionary architecture. And it doesn't mean don't do any design and just see what happens, but instead that you're like in a state of constant design and iteration, that you're doing more, not less design to enable growth and change. And once you start thinking about that, you realize that the truism is that the best design you can come to is the one that is easiest to change. That's it. That's all you got. And you know what? That's kind of freeing. Like, it frees you from perfection. Like, all the perfectionists can like breathe a sigh of relief because you kind of don't have to get it right. You just have to kind of get it right enough for now. Taking a good educated guess, though, at which aspects of your system might be exposed to like additional load or feature creep or changing requirements is like a useful tool you can build on. Like, you can build abstractions to contain those kinds of concepts. Now, that doesn't mean like build open-ended extensibility points everywhere through your software. You know, that's over-design normally, but it does mean you should make sure that wherever you expect your design might shift or flex, that you should be careful not to let assumptions from your earliest version creep into like the core of the system design. That's the tool you have. So one of the few useful things, probably one useful thing I ever heard Jeff Bezos say, and go on record, one nice thing about good old Jeff, is to paraphrase that there are two types of decision. There's like a category A and a category B decision. And basically one category of decision is the decisions that are easy to unmake, cheap decisions. Make those recklessly, frequently, don't worry about them. The other type of decisions are decisions that cost you like 10 times the amount to unmake when you make them. And when you're doing the first phases of your design, try and avoid making those decisions, because those are the things that bite you later. So the final superpower in building a design that's fit for growth is to name your things, right? Come up with language. I love language. Language is how we form thoughts. So my organization has like 60 engineering teams, and one of the most important things we did, we build APIs, and we just gave the kinds of APIs we build names. It sounds really simple, like this one simple trick. We build domain APIs where behavior lives, right? Very simple. We build connector APIs, anti-corruption layers against third-party systems. We build composite APIs that marshal processes across multiple domains. And you know what? Giving those styles of APIs different names was one of the best things I did to help communication with our product teams, because I kind of gave them things that they could latch onto and they could tap the sign. And I know it sounds simple to say, hey, build a ubiquitous language, kind of DDD coded. You know, the DDD community learned this decades ago, and it somehow was lost in architecture. So in fact, as the systems I have been looking after have kind of grown and found their shape, I found it useful to like embrace sloganism. So depending on what we're trying to get done at a certain like time or phase, I come up with different catchphrases that I say for like 3 or 6 month periods. So this, capabilities, not customizations. So that was because I was trying to guide the teams away from a place where they're doing client-specific work into building generalizable features that we could sell to different kinds of people, right? And that was the summation of that. Designing for substitutability, to capture the idea that we were operating in like an enterprise ecosystem where our partners would want to bring their own subsystems like identity, substitutable systems. Or even just building a boring platform, right, to help lock people in on the idea that we were doing boring web standards for everything. Only standards, boring, predictable. People should look at it and go, well, of course it's built like that. And so as your system grows, finding language to characterize them, you know, it makes it easier for the people making moment-to-moment decisions, right? And that's really how we make good design happen. So I spent a long time talking about the subtlety of this process of design, but with something so often seen as subjective, people often try and find the science behind it. Now this book here, by way of reference, so this is written by Barry O'Reilly. He's spoken here before, I think. He's been talking and writing about what he calls residuality theory for the past 4 or 5 years. And to crudely sum up 2 entire books of his, It's the process of simulating evolutionary design to try and find the design that's most resilient to stress. So he basically games out designs, applies different breaking characteristics, and those designs leave behind what he calls residues of the system, and effectively you add enough stress to the system, and over time, one of those designs recurs the most, right? And he's basically come up with a method to measure and simulate where the best possible design from what you know now lies. It's really, really cool. It's probably the most interesting work in this space in like a decade. So as we wrap up, I just want to tell you a story about something that I found personally inspirational when it comes to making beautiful designs. And it was going to like a Tim Burton art exhibition. So there's this concept of regular form. Now, it comes from language where it kind of means the collections of idioms and defaults and standard ways of doing things. And people love to use regular form because we're conditioned to see meaning in patterns, right? Like humans are big old pattern matching machines. And I think the interesting thing about software is software has lots of regular form in it. But the designs that often take the strongest hold, often they break with regular form, right? It's super interesting. So I always use the MVC pattern in web dev as an example of this. Now, in most frameworks, like especially in the .NET space and the Java space, the MVC pattern is implemented as classes. Now, classes are meant to be collections of data and objects. An MVC controller with like action methods isn't really a class. Like it doesn't fulfill any of the semantics of a class at all, but it's so obviously a nice visual metaphor for the way you route web requests that it just kind of stuck, and nobody was like, it's a weird class, isn't it? I think it is a weird class. And we subvert regular form because we got a good design from subverting regular form. Now, I think the reason is kind of interesting. So I think, what does this have to do with Tim Burton, right? So I went to this exhibition, and what I didn't realize when I went in was that Tim Burton started off as a traditional hand animator. And you know, he's famous for all of this kind of stuff, right? Big, elongated, everything. And I went and I looked through all of his university sketchbooks, and they are the most card-carrying, default, perfect, traditional anatomical studies of like human animation and locomotion and bodies. Like the most default Disney, Hanna-Barbera, everything. And it occurred to me that like the reason Tim Burton got here is because he gained such a deep understanding of regular form that he could subvert the best aspects of it to more correctly capture the kind of the intent of the work that he was trying to put out there. And I think if he hadn't had such a perfect grasp of traditional animation, he could probably never have designed his signature style because he wouldn't have known which thing he was trying to solve for. And I thought that was kind of beautiful and inspiring that like you can of course subvert regular form, but if you do it, make sure you're doing it with a lot of intent to like better nail a problem that you think is so much better than the traditional way of doing things that it's just like obviously correct. So I thought that was kind of cool. So yeah, basically what I'm really hoping over the next decade or so is that software design sees this kind of renaissance, right? That design that's done by everybody. And perhaps it's the thing that maybe will humanize and re-legitimize software architecture as a discipline by kind of shaking off the pretentious kind of historical artifacts of ivory tower architects and making it something that we just all accept that everybody does all the time. Because if we can find a good language for this thing and become more mindful about the explosion of complexity driven into systems by like the prevalence and availability of just pouring more technology into the fire and just sending Microsoft another $100,000, we'll end up with the like much more ergonomic and beautiful and fit for purpose systems that have a better chance of surviving, right? Like I guess I foundationally just think we should build smaller things, like smaller, more beautiful things. And that's because your software has a design, whether you intend for it or not. And that's me. Have a good rest of your conference. 10 seconds to go. Look at that.